This is the first part of Lecture 11 on ultra-wideband technologies. Lecture 11 and Lecture 12 are categorized as system aspects lectures. These lectures basically are going to take advantage of a channel modeling knowledge that we had earlier, and also modem design technology knowledge that we had earlier, to describe systems and trends of technology. The trend of technology today in wireless networks is the so-called location-aware broadband ad hoc sensor networks. These are the key technologies of the future wireless. And ultra-wideband technology actually provides one of the major tools for implementation of these networks, the way that is perceived today. Ultra-wideband provides better positioning, which is related to that location awareness for accurate positioning, in particular in multipath rich environment, like urban and indoor areas. But we have a separate lecture on that, so we don't get delved into that. The other one is the issue of the wideband or broadband, higher speed. Ultra-wideband communication, you can go up to data rates which are close to hundreds of megabit per second, which are necessary for video communications, which are going to be the next hurdle of wireless communication for local application like home networking or home theater scenarios. So people have a lot of hope on ultra-wideband toward that direction. And then also ultra-wideband is low power and local, which is very suitable for emerging ad hoc sensor networks. So basically, ultra-wideband technology has attracted a lot of attention for all of these elements of emerging wireless networks, which is location-aware, broadband, ad hoc sensor networks. So for that reason, that's very good. And then in this lecture, we try to have some understanding of ultra-wideband communications and what is the difference with that and how it is applied, and how people do the channel modeling for that. So the way that I want to cover this material, first I give you an introduction, then I talk about channel modeling, then I talk about ultra-wideband systems. There are basically, for channel modeling, path loss and multipath model. For ultra-wideband systems, we have three proposals, if you want to call it: impulse radio, direct sequence ultra-wideband, multi-band actually, MB, or multi-carrier OFDM. And we have seen all of these technologies before, except possibly impulse radio. But even impulse radio, we have seen it before, as we can see later. But this is a new packaging of those technologies. And it's a good overview. So we start with introduction. What is the history of ultra-wideband communication? The first technique used for ultra-wideband, what we call today ultra-wideband, is the so-called impulse radio. And impulse radio really existed in military since 1950s for like radar type of applications. And the story is that in normal communication, what we do is we have a pulse, we modulate that on a carrier, and then we send the pulse. In impulse radio, we send the pulse without modulation. So it's low power and easy to implement. And that type of application were popular in the radar. Now, the first patent for communication using impulse radio is reported in 1973, which is like first time that impulse radio becomes a communication tool. Then later on, around mid-1990s, as I mentioned in other lectures, this project Bodyland started in BBN here in Massachusetts, supported by DARPA. And that particular project motivated really what we call WPANs, wireless personal area networking type of application. And in 1997, a specification of the Bodyland became first specification for 802.15. This 16 again have to be 15. And then, however, as soon as they came with that application, Bluetooth got released, and Bluetooth ended up to be 802.15.1, the first standard for the so-called WPAN, wireless personal area networks. And then immediately, Bodyland by itself, when they were studying the Bodyland, they were putting a lot of emphasis on low power, and they were considering pulse transmission as one of the solutions. Okay? But as we all know, Bluetooth was a frequency hopping system. Now, around the same time, ultra-wideband technology was emerging for this type of application under DARPA's military projects. And somehow it got influenced in 802.15 and started 802.15.3, which was supposed to be a WPAN with higher data rate. Bluetooth has data rate of up to 700 kilobit per second, but which is good for voice application and a lot of local applications, like networking inside a car. But wherever you are talking about video, that data rate is very limited. So people were thinking about higher data rate for, like, as I have mentioned many times, for video transmission and home scenarios. So this 802.15.3 started to go after higher data rates. And then wireless LANs at that time are going like 54 megabit per second, and they are looking at 100 megabit per second. So in order to have an identity, they are looking for data rates which are above 100 megabit per second, really. But it could be in very short distances, like wireless USB type of application. So this is where this industry is heading right now. And then the group which is trying to do the standardization is 802.15.3. And this group is motivated by ultra-wideband technology. And the first ultra-wideband technology is impulse radio. However, you need, again, ISM bands, something similar to ISM band, unlicensed bands, because the bandwidth for ultra-wideband is in order of several gigahertz, and nobody can afford to purchase those hours, so it has to be ISM band, similar to ISM band, unlicensed. So they start these activities of 802.15.3 close to year 2000 or a little bit earlier than that, but immediately they go after the frequency bands and negotiation with FCC, and impulse radio technology, the original one which comes in, occupies a frequency band, as I will show you earlier, from 0 almost up to 5 gigahertz. But FCC refuses to give those bands out. So the bands, ultra-wide bands that FCC releases, starts from 3.4 gigahertz up to 10.6 gigahertz, as I will see later. And that one challenges the impulse radio, because now you have to change the mask of the filter, and it becomes more challenging. And then 802.15 actually endorses two other solutions, which one of them is direct sequence ultra-wideband. The other one is multi-band ultra-wideband. Multi-band, this one again needs an M. Multi-band OFDM. So basically we have like three technologies there: traditional impulse radio, direct sequence ultra-wideband, and multi-band OFDM. It's not a surprise. We have seen that direct sequence spread spectrum was the dominant technology for 3G cellular networks. So apparently now that new technology, new band becomes available, we want to repeat that success. And OFDM is not surprised, because OFDM was the survival of all the fights for wireless LAN technologies. So finally, wireless LANs, starting from direct sequence spread frequency hopping, they go to CCK, but they land into OFDM for broadband. So we have two camps, really. The camps perhaps with a little tendency towards cellular, and a camp with a little bit tendency toward wireless LANs. And those two proposals comes to 802.15.3. And then the band that we have available is 3.4 to 10.6 gigahertz, which finally got released in 2002. And today, people are trying, there are several small startup companies, they are trying to develop technologies, but as in the case of wireless LANs, technology is not the hurdle, and the challenge is the application. So people are trying to find applications for which they can successfully generate enterprise in these frequency bands, really. That's the status. A lot of people, they get engaged into this type of argument, technical argument, that I have seen that over past 2 decades, that has been useless, really. It's not the matter of technology, it's the matter of developing application. And the applications that I see emerging as this line are the ones that I told you. One is when you have very, very wide bands, you expect that you can generate technologies which give you accurate positioning. And the other one is that when you have such a big band, you can support multimedia video coverage. Okay. And people are around that type of application. And we describe the technology. These are different working groups in 802.15. I talked about group 1A, which was the Bluetooth. Group 2 was coexistence, which is now not active. Coexistence was basically interference between Bluetooth and 802.11. It was very popular for a while. At the heat of Bluetooth, that was one of the most popular groups. And then 3A is WPAN at high rates, which is ultra-wideband, and the one that we are interested in. 3B is maintenance. Publicity committee is not as of our interest that much. Then is group 4, which works at low rate physical layer. This group 4 is also referred to as Zigbee, and actually is very popular. Because as we saw in the first lecture, a lot of these like sensor attack network type of applications are low speed. And to have low speed, low cost, Zigbee is a very good. They are in a better position in terms of generating commerce around them. So Zigbee is very popular now. And actually they have a conference like next week or something around it, somewhere in Paris or somewhere. So, and they have a lot of conferences. And this area, which was technologically is not very challenging because it's low speed. The data rate is up to 250 kilobit per second. Okay. And doesn't provide very accurate position. But within the Zigbee also, some people are trying to look into ultra-wideband technologies. But anyways, we are not talking about Zigbee much today. And then they have this group 5, which is working on mesh networking. Among all of them, we are interested in group 3A, which is high data rate, because this is the one which pays full attention to ultra-wideband technology. Then 802.15.3a, basically frequency of operation, is the entire band which is available for ultra-wideband. They are looking in data rates which is from 110 megabit per second to gigabit per second. 110 is more than what 802.11 sees up to wherever you can go. That creates an identity for the group. And ranges, however, as I increase the data rate, I have to reduce the range. So these guys are talking about ranges up to 10 meters. Ranges up to 10 meters are good for applications like wireless USB, for example, but for home networking, you need more than that. And for a lot of more applications, you need more than that. But anyways, people are developing around this idea. Another issue for 802.15.3a is that when you have ultra-wideband, everybody thinks that the wider the bandwidth, you have more accurate positioning. So they expect that they will have more accurate ranging. And this is, again, a debacious issue that if I had time, I will discuss that in the lecture on positioning. Now, then, but anyways, this is the general perception. Wider the bandwidth, better the resolution. And better the resolution, you have more accurate positioning. Now, there are three solutions that I told you. Impulse radio, which was a traditional one. And then multiband OFDM and direct sequence ultra-wideband. Typical applications that people are thinking of for the 802.15.3 are like wireless USB that I mentioned, wireless multi-channel high-definition TVs, home networking, and then accurate positioning, like for firefighters, for medical equipment inside the hospitals, to tag children. But remember, if I want to go to 10 meters, it's very difficult to do this type of thing. Because if you want to locate a firefighter inside a building, which is like 50 by 50 meters, and your coverage is 10 meters, you put your sensors outside, you cannot locate them. You don't have coverage. So these are the challenges, actually, that people are doing research on that, both at WPI and at University of Oulu. We have research groups, and I think they are doing leading work in this area currently. And I will give you some of that in my next lecture. Then comes the issue of ultra-wideband for wireless sensors, the buzzword. These sensors, as I showed you in some of the applications in the first lecture, people are thinking about ad hoc network formations. Like you have these mines, little mines, that they communicate with one another and move. And when one of them is blown, the others, they see each other's. Or there are sensors all over the place to detect chemical, like whatever type of chemical or radioactive material or whatever. And these sensors are very inexpensive and small, and they're communicating with one another. And they form a very large, huge network that has failure, because part of this sensor, they lose the battery, they get blocked, somebody walks over them. So they have to be self-healing. They have to come back and communicate with other. But anyways, so ultra-wideband technology is considered for that type of applications, especially in particular by military. For military, the issue of security also comes to the picture. The wider the bandwidth, the easier to provide security, because your power gets more spread over a wider area. So for the sensors, which as of now, most of the applications are related to military and security, they need low interception and low detection. Low probability of interception, low probability. And these are and anti-jam. These are basic military requirements. Okay. Also, they want them to be low power because you want to throw a sensor and leave there for like 3 years with one little battery. And then they need to have embedded antennas, small antennas. Size should be small. They have to be low cost because you want to distribute a lot of them. And they have to have like energy efficient routing. And ultra wideband waveform is going to have, is good for all of these things. In addition to that, it can provide accurate geolocation services. Now, for sensor networks, actually, one of the issues, current issues, is the issue of I have now like hundreds of sensors in a building, and they are pumping a lot of information, and I want to process this information. If I don't know where these sensors are, processing of information is difficult. So again, those people who are working on RF, like ID type of applications, which are several groups actually, one active group in MIT right now that they are trying to influence. These people are very keen as next generation of RFID to look into positioning, indoor positioning for RFIDs, and then that brings again ultra wideband as a good solution, at least to their eyes. But what will happen, we don't know. Okay, because industry always evolves unpredictable, at least in this field. So with that, I also want to talk about like frequency band. The actual frequency bands which are released by FCC are these bands. It comes up to 0.96 gigahertz and with a higher allowable power spectral density. Then it goes low, and then it has some glitches, and then at 3. Actually, this should be 3.4, I believe. 3.4, it comes again to minus 41 dB up to 10.6. And this band, which doesn't go up and down, is the band that people in 802.15.3a are interested in, while these other bands are also available, according to FCC rule. Now, if you get this band from 3 to 10 gigahertz, let's say, for ultra wideband communications, and you want to compare it with other systems that we were looking into them, we want to use this band for ultra wideband and WPANs. But before they come to the market, we have cellular band at 900 megahertz, and we have PCS bands at 1.8 gigahertz. And then we have ISM bands, one of them at 2.4 for 802.11 BG. And then we have ISM bands at 5 gigahertz, which are for 802.11a. And if we look at all of them, certainly power in the cellular and PCS is more than wireless LANs. But none of these guys are interfering with this channel. The only one which interferes is 5 gigahertz bands. And 5 gigahertz bands are which one? 802.11a, only one. And this is good to notice because we see that now the systems which are like going to 802.15.3a, they try to somehow take care of this guy, somehow accommodate that. And they find some neat engineering tricks to somehow avoid this band. So this is like an introduction about like what is ultra wideband and why it is important and why it attracted attention. Now, the next topic would be channel modeling, and before we go there, we want to do a little bit of technical evaluation of ultra wideband, because everything that I told you up to now was non-technical in a sense. the first thing is that what is the significance? What will happen if I have ultra-wide? What is the meaning of ultra-wideband? Means that my bandwidth is like over 1 gigahertz. I mean, if you want to compare like TDMA systems, bandwidth is 200 kilohertz. That's GSM. IS-95 is 1.25 megahertz. And then if you go to like wideband CDMA, it is like 5 megahertz. Okay. If you go to wireless LANs are like around 20 megahertz. But this guy suddenly goes 20 times, 20 times, no, 50 times more than that. Like 1 gigahertz and even more than that. So what will happen if I have such a wide band? What will happen really? Well, the first thing that I'm concerned is receive signal strength. Receive signal strength, you remember this equation. This equation was the received power in terms of transmitted power, which is a function of f, frequency, because this lambda is a function of f. If I put rather lambda, it's c over f, okay, I get this equation. Okay, this equation, this is the gain of the transmitter, gain of receiver, transmitted power, these are constant, this is the distance, this is the speed of light, f is the only variable in here, which is the frequency of operation. Normally, when we were doing our calculations for all the systems, we were assuming that this f is what? F is your carrier frequency, which is center of your bandwidth. But in ultra-wideband, this approximation is not that correct. Because if I have the bandwidth as only a fraction of carrier frequency, this is a good assumption. Otherwise, it's not. Let's see what will happen. If I have the power at different frequencies, the total power I have to integrate over f. So I integrate this function over f between fc minus w over 2 and fc plus w over 2. Means from the center frequency, I go w over 2, half of the bandwidth on the left, half of the bandwidth on the right. If I integrate that integral, if I calculate that, this is going to end up to something like this. And if I do the detail of calculations, finally it ends up to this number, which is P transmit on the average and GRGT C2. This is lambda square. If I look at this part really is the power that I was always using for what? For narrowband communication. This is exactly the same thing that I had in here. Whenever rather than f, I put fc, this is the received power for narrowband communication. Okay? Then I have this factor on top of that. Okay? So totally, my ultra-wideband power is this thing, which is narrowband power, times this thing, which is 1 over 1 minus w over 2fc. So let's say that if my bandwidth is like 1 megahertz, so that I'm like IS-95, 1 megahertz. Carrier frequency is around 1 gigahertz. 1 megahertz over 2 gigahertz is like 0.005. It's a very small number. I square that, it gets even smaller. So this thing is almost 0, and my average power is the same as power of the narrowband, power of a carrier. But in ultra-wideband, I may have 5 gigahertz bandwidth, and FC could be just middle of that. If FC is the middle of that, let's say, I have 4, let's say, assume that W is equal to 4, let's say, gigahertz. So my band is from here to here, from 0 to 4 gigahertz. And then the center in here, FC, is then equal to 2 gigahertz. Let's get the number, see what will happen. The number that I have is W over 2FC. W over 2FC, W happens to be what? 4 gigahertz. 2FC is another 4. So this one gets close to 1. So what will happen to the receive power? Receive power for ultra wideband is receive power for narrow band times 1 over 1 minus W over 2FC square. And if this one is equal to 1, this is 1 over 0, which is infinite times more. So with ultra wideband, I have more efficient communication then. With the same average power, the ultra wideband power is going to be what? Much more. Okay? So that's one of the incentives in there. Okay? So, but this 4 over 4 never happens. This is the ideal case that I have something like this. It gets close to that. So the issue in here, just like any filtering and anything like that, I'm a function of W over 2FC. My efficiency of transmission of the power increases with this value. Okay? If the bandwidth is narrow and FC is high, I have 1 minus this thing, which is the same as 1, close to 1. As W becomes larger with respect to FCC, this number goes towards 0, moves towards 0. And my efficiency becomes better and I send more power. So this is one technical good part of doing what? Ultra wideband. So that would be one incentive to go for ultra wideband. Okay? But like anything else in the life, we have always pros and cons. All the calculation that we did there assumes that we have the same antenna gain for the narrow band and wideband. If we have the same antenna gain, ultra wideband is more efficient. That's one thing that we showed. The other thing that we saw for ultra wideband is that it supports higher data rates. Because I have wider bandwidth. If I have wider bandwidth, especially in data communication, it's a multi-rate environment. When I'm coming very close to the transmitter, I have a perfect channel. So I can go to very high data rates. And since I have up to 1 gigabit over gigahertz bandwidth, theoretically I can go to gigabit per second. So that's the second advantage. So it's power efficient, so I can have a multi-rate environment, I can have very high data rates. And I know there are applications for that. Like, USB ports, wireless USB. I can put them very close to one another, but I don't want to connect them together. And then provides for a better resolution and ranging. Because the wider the bandwidth, the narrower the pulses, I'm resolving more of the multipath. And if I resolve the multipath better, I will have a better. In addition to that, that's in multipath environment. If you go to like non-multipath environment, if you have like additive noise. In additive noise channel, also there is Kramer-Raoul bond, which shows that as you increase your bandwidth, you have a more accurate positioning. So these are advantages, beautiful advantages of going to wider bandwidths. And ultra-wideband we refer to like gigahertz, around gigahertz bandwidth. So what are the things that we lose? I mean, if it was that good and that easy, how come people were not doing that from day one? Now, things which are against ultra-wideband, one is antenna design. If I want to design an antenna which has the gain, flat gain, over a wide band, it's very challenging. Similar to filters. It's always very challenging to design a very, very wide band filter. So if you have W over FC is small, it's easier to design for the filters. So you can have first order filter if W over FC is easy, is small. If W over FC is large, filters are going to be very challenging to design. The second issue is that if I want to go to those like gigabit like type of bandwidth, I have to go to higher frequencies. If I go to like several gigahertz as my center frequency, then penetration through the walls becomes less. So in most of these applications that I'm talking about WPAN, my coverage becomes limited. The next thing is that I'm talking about more resolution coming out of ultra-wideband. I will show you that a little bit later. This is something new. I don't think there is in any book or paper, actually. It's new stuff that I will show you that this perception that if we have wider bandwidth, we have more accurate positioning, is at the expense of sacrificing the coverage. Coverage even for positioning, not coverage for communication. Okay. Which what will happen is that normally I have like several paths, they combine together, they give me a stronger path, which is my first path that I want to estimate. When I just isolate these things, I have a smaller path, so I cannot cover more. I will show you some figures on that later on. So coverage for positioning becomes more restricted for ultra-wideband. Then, if I'm designing these things, these days everybody wants to design digitally because it's less expensive, it's more controlled, and here and there. With ultra-wideband, I have to sample the things at least like at Nyquist rate, twice that. So that's a challenge. Implementation would be a challenge. But that challenge has been answered very, very reasonably with the emerging implementation technologies in the past few years, and MEMS, etc. Nanotechnologies and the MEMS and this type of thing are helping to resolve that particular problem. Okay. So up to here, what I did, I gave you an introduction. In this introduction, what I did, I talked about pros and cons and incentives for using ultra-wideband technologies. I think we can take a short pause and start our next lecture in the next video.